Then let's start. Our next speaker is Professor Toshiyuki Kobayashi of the University of Tokyo. He will talk about branching problems and the global analysis of locally symmetric spaces with indefinite metric. Please welcome.
Thank you very much, and thank the organizers for making all the effort to make this event possible. So this is a plenary lecture intended for a broader audience with different mathematics backgrounds. I try to make my presentations as accessible as possible, and by illustrating some simple examples. But on the other hand, the full generalities of the result, sometimes I put at the bottom of the slides the references to each theorem. Okay, so let's start. The object of my talk is about spectral analysis on the double coset manifold beyond the Riemannian setting, where there is a Lie group and H subgroup, and gamma is a discrete subgroup. If the axioms of gamma is nicely on homogeneous spaces, and then we have a covering so that all the local geometric structures can be pushed forward to this manifold. And we are particularly interested in the analysis on this manifold by what we call interesting differential operators, such as Laplace-Boltzmann operators in this non-Riemannian setting. Special cases of this problem is already a long history and deep and rich. For example, so this is classical features for SL2R case, but there are some very special cases, such as G is abelians, or gamma discrete group is trivial, or the subgroup is compact. But each special cases have a long history on these questions. For example, in the abelian case, if we consider flat Riemannian, but indefinite cases, and then the spectrum of the Laplacians is a set of the evaluations of the quadratic forms of indefinite on the lattice point. And this is, for example, connected with the Oppenheim conjectures in analytic number theory, and later proved by Daniel Malouis. And in the case gamma is trivial, and then spectral analysis is related to the Plancher type theorem that is decompositions on regular representations L to the model H, which is initiated by Gelfand school and Heischendras for the group manifold, and then for the symmetric spaces by Helgason, Fersensen, Hoshima, Delam, and some others developed this harmonic analysis. This is the case when discrete group is trivial. And then, on the other hand, if H is compact, but gamma is an arithmetic lattice, and then this problem is closely related to the local theory of automorphisms, and then also these are some names that developed this problem. So very special cases already has a long history and deep theories. But what we want to do is a new challenge that gamma group is non-abelians and discrete group is non-trivial, and then the subgroup is non-compact, so beyond the Riemannian setting. So then, in addition to the traditional difficulties, there exist arises further difficulties. For example, so this further difficulties include geometric difficulties, analytic difficulties, and also representation theoretic difficulties. For example, for the geometric difficulties, we have to think about if there's a nice manifold or not, and this relates to the questions from local to global beyond the Riemannian setting. And also analytic difficulties includes, for example, intrinsic differential operators such as Laplacians is no more elliptic differential operators. So we have to deal with a different type of differential operators. And also for representative theoretic difficulties, if H is non-compact, and if the double coset space is the Hausdorff, and then always the volume of Z mod gamma is infinite. And this means that the regular representations on the function space on Z mod gamma is not well under control in general. So these are new difficulties by this much general setting. And so to overcome these difficulties, we need some new machineries and also new geometries. And so in this talk, the first half is about constructions of new geometry for the studies. And so this is includes that if local to global theory beyond the Riemannian setting, and then how to construct such a nice manifold. And then also we discuss about rigidity problem and also deformation theory on such a space. So this is a half part about geometry, new geometry. And if we have a new geometry, and then we are interested to think about the global analysis on such a new geometry. But there's new difficulties, and so we bring some new machineries. For example, we utilize branching theory of unity representations into the spectral analysis on this problem. So this will be topic C and topic D. Okay, so so roughly speaking, the half path is about geometries. And so first we want to construct some geometry, and then also we think of the deformations, something like longer strings or shorter strings, what this means. And then the latter half, we talk about global analysis on these geometries. Okay, so the topic A, topic B is about geometry. So this is constructions of geometry and then deformation theory. And then we discuss about the analysis. So first we discuss about the new phenomenon that arises beyond the traditional Riemannian setting. And then we explain some new method to capture all the spectrum. So this is my planning of the talk. Okay, so now let us discuss the first half of the geometry. So, but as a warming up, that we recall some classical traditional Riemannian geometries. So the study from local to global in Riemannian geometry has been a major trend in differential geometry over the several decades, so since 20th centuries. And but as a warming up, we may recall one of the most classical theorems due to Bonnet and Myers, that saying that on complete Riemannian manifold with positive Ricci curvatures strictly larger than some constant is compact and diameters is bounded. So this is a very classical theorem. But then we want to go beyond the Riemannian geometry where there's no metric. And then we may ask ourselves that how about the local to global theory in pseudo-Riemannian geometry, such as the Lorentzian manifold. Here we recall some basic terminologies. A pseudo-Riemannian manifold is a manifold equipped with a non-degenerate symmetric bilinear form at tangent spaces. And then, so the signatures PQ, so P plus Q is the dimension of the manifold, is locally constant. And the Riemannian manifold means that this Q equals 0, and the Lorentzian manifold is Q equals 1. And similarly to the Riemannian manifold, that one can define Laplace-Berthelin operators. It's a second order differential operators given by gradient composed by divergence. And such an operator is well defined, but it's not elliptic differential operators if it is indefinite. And so we have to deal with a different type of analysis. Okay, now back to this local to global theory in pseudo-Riemannian manifolds. one of the most classical results is due to Calabi and Marcus about 60 years ago, saying that any Dugita manifold is compact. Here, Dugita manifold is a Lorentzian analog of sphere, namely Lorentzian manifold with constant sectional curvature, positive 1. And this manifold is an example of space form in pseudo-Riemannian manifold that we discuss in a more general setting in the next slide. So suppose that M is a pseudo-Riemannian manifold of the general signatures. And then we say that MG is a space form if its sectional curvature is constant. And this is a model space in the case sectional curvature is 0. So this is a flat vector spaces endowed with standard metric of indefinite metric. And then we consider its hypersurface given by this quadratic form is constant to be 1, for example. And then this is a pseudo-Riemannian manifold of a signature PQ with positive sectional curvatures. So this is an analog of the spheres. And if we switch the signatures of the ambient space, and then we get a space of negative constant curvatures. So this is one way of the construct a model space of constant sectional curvatures. But in this case, indefinite orthogonal group acts on the ambient space isometrically and leaves its hypersurface invariant. And so it also acts on this model space. And actually, its actions is transitive. And so the model space is also interpreted as a homogeneous space of the D groups, namely this D group modulo OPQ. So this is another interpretation of the constant curvature space. So this is semi-simple, so-called semi-simple symmetric space of rank 1. Okay, so still I continue warming up. So this is an example of space forms. So in the Riemannian manifolds, as you know, that the sphere, Euclidean space, and the hyperbolic space are space forms of positive, 0, negative constant curvatures. And in the Lorentzian manifold, De Sitter space, Minkowski space, and anti-De Sitter space is space form of positive, 0, negative curvatures. And also, alternatively, one can write it as expressed as homogeneous space, so symmetric space. And another example is two-dimensional case. So the model space is compact only when it is Euclidean spheres, but by taking appropriate discrete group of isometries, we may get some compact form in the Riemannian case. So this is a compact Riemann surface endowed with negative constant curvatures. But in the Lorentzian case, the situation is completely different. Namely, there does not exist compact two-dimensional manifold having Lorentzian metric and constant curvature positive or negative. Only zero curvature case there exists compact form. So this means that the global nature of the manifold depends on the local geometric structures. So we may formulate such equations. So this is what we call space form problems in pseudo-Riemannian geometries. So this is a question from local to global problem. Local assumptions is that fixed signatures for pseudo-Riemannian manifold PQ, where the P plus Q is the dimension of the manifold, and then fix the signature of the curvatures. Then we may ask, what is the global nature of the manifold? For example, do compact forms exist or not? And also, what kind of groups can arise as their fundamental groups? And these questions, for the last several decades, there's a lot of work on this problem, but still complete answers, even in this case, are not known so far. And we shall see some state of the art of these questions, but also in a more general setting. And so these questions can be understood, interpreted in a group language because of this uniformization theorem. Namely, any complete pseudo-Riemannian manifold of signature QP with negative constant curvatures is always of the form of the double coset space, where G is a Lie group, indefinite orthogonal group, and H is a OPQ, as we saw before. And gamma is a discrete subgroup of the isometry, but acts proper discontinuity and freely on this space. And so this actions of proper discontinuity actions give some constraints of the global nature of the manifold, as we shall see later. But in the traditional case where H is compact, then any discrete group acts proper discontinuously. And the special case of the case when H is compact is the classical theorem, uniformization theorem, Klein-Poincare-Kebe, that any compact hyperbolic manifold, two-dimensional hyperbolic manifold, so compact Riemann surface with genus G greater than 1 is obtained as a double coset space of this form. And so then questions about constant curvature space is interpreted essentially by means of the group language of the triple of the G, H, and gamma. Okay, then we want to formulate for a more general setting. And for this, we need some terminologies. So we recall the continuous actions of a locally compact group acting on a locally compact space is called proper if the action map is a proper map, in the sense that the full inverse of the action map of a compact set is still compact. And the properly discontinuous actions is nothing but the proper actions when the group itself is discrete. And so proper actions is the most important thing to understand in these questions. Then general setting, now we don't have to think about a special case like a constant curvature space, but just a general case that we consider G to be a Lie group and H a closed subgroup and L is another closed subgroup. Then the most important problem to understand local to global is that what is the criterions where for the subgroup action L on Z mod H is proper or not. And if H is compact, then this is automatic. But if H is non-compact, then this is not automatic. So we want to understand when the actions L on X is proper. And for example, when L is a discrete group, and then we want to understand when this happens. And these conditions of the proper actions, we symbolically write this kind of transversal conditions in a non-commutative group Z in a coarse geometry. We can give a precise definition, but here just we use this as a symbolically generalizations of the proper map. Okay, so we want to find the criterions. And this question is still unsolved for general Lie groups, but when G is a reductive Lie groups, then we have a complete answers to these questions that we recall now. So let G be a real reductive Lie groups, such as GL and R. Then one can define Cartan projections from the reductive groups to the Euclidean space, maximally split abelian subspace by using the Cartan, so-called Cartan decompositions. But I give illustrated by examples. If G is GLNR, then this map is a map from GLNR to Rn up to permutations, given as follows. Take any matrix, n by n matrix, and then we consider transpose of the matrix and multiplied by G. And this is a positive definite matrix, and so all the eigenvalues are positive. And then we take a logarithmic. And then, so this is a map. And then permutations of the eigenvalues up to permutation of the eigenvalues, this is a well-defined map. So this is a Cartan decomposition. The important thing is that this is a highly non-commutative group, but the image is abelians. And so we want to use this as a transitions from non-commutative one to abelian. Then here is the criterions. So namely, take a subgroup L and H, and then the actions L on Z mod H is proper if and only if we can detect it by the image of the Cartan projections. So the actions in here is very difficult because G is non-commutative, but A is abelian, and so once we get them Cartan projections, then we can detect whether or not the Cartan project, the action is proper. And this theorem is proved by Benoit and by myself as extensions of the case when both L and H are reductive subgroups. And in this talk that we shall use this theorem as a key machinery, for example, deformation theory of the discrete groups, and also counting of gamma orbits in the pseudo-Riemannian geometry. Okay. Now, let us fix some basic notions. Discontinuous group. So again, that we consider the triple of the Lie groups, and then the right coset space and the left coset space are Hausdorff manifolds. But if we consider the double coset space, and then the quotient topology is not necessarily Hausdorff. But if the gamma action is nice, as we saw before, namely, if gamma acts properly discontinuously and freely on X, then this becomes a Hausdorff manifold, and this is a covering map. And so, in such a case, we say gamma to be a discontinuous group for Z mod H. So historically, that sometimes that discontinuous groups and discrete group is used in the same meaning, because historically that traditionally that people consider when H is compact. And in fact, that if H is compact, then gamma acts as an isometry on invariant metric. And in general, that discrete group of the isometries acts properly discontinuously in a Riemannian geometry. But if the metric is indefinite, then the discrete group of isometries may not act properly discontinuously in general. So this is a difficult and a new difficult point. And so we use some precise notation, notions that the discontinuous group means that it acts properly discontinuously and freely. Okay. And then in the special case, we are constant curvature case that there are many works on this local to global geometry. And this is some state of art of these questions. But still, some new results are going on. And but I just give some what is known. And so first is what we mentioned, Karl Marx phenomenon and its generalizations. So namely, this space, or look, this means that we are thinking the space form problem for signature QP and negative curvature space. And then there exists an infinite discontinuous group if and only if P is strictly smaller than Q. And Calabi and Marcus consider the case when Q equals 1. And so this condition fails. And then they prove that any discontinuous group is a finite group. And this is now if and only if conditions. And also some of the homogeneous space admit some large discontinuous group, such as a co-compact discontinuous group or co-volume finite discontinuous groups. For example, so this is a hyperbolic manifold. So this is a Riemannian case, and this is a sphere case. And this is a Lorentzian manifold, and this says that the odd dimensional Lorentzian manifold with negative curvature, namely anti-Dogita manifold, odd dimensional anti-Dogita manifold has a compact form. But actually, even dimensional one doesn't have a compact form. And the last one, for example, says that there exists a 15-dimensional manifold of the signature H7 with negative constant curvatures. And so some of the geometry has even compact forms. But also, not all of them have a compact form. For example, so this is the necessary conditions to have a compact discontinuous group.
And these all of them for number 3?
Conjecture.
Exactly.
It's a conjecture. And I'll explain even more general conjecture that covers this one. And also give some history. Thank you. Okay. And also we can think of the more general cases that G is, for example, reductive groups and H is reductive, so that G mod H has a pseudo-Riemannian structure naturally by the killing form. And then we may ask that for such a local geometric structure, which gamma is allowed? For example, if there exists an infinite discontinuous group exists or not. Also, if there exists a compact model exists or not. This will be topic A. And then also we may think about deformations of such a spaces. So this will be treated as topic B. Okay. And the first questions in the case of the reductive case is completely solved by the previous criterions. And actually that it is written by means of the real rank of the groups. And so we focus on 2 and 3. Okay. And so now we enter topic A. So so far we have a warming up. And then we want to talk about existence of obstructions to have a nice geometry. And the simple way is to think of the arithmetic subgroups of the reductive groups. And this theory is developed a lot in the 60s by Harishchandra Mosto Tamaga. And for example, SLNZ in SLNR. Then any such a group is covolume finite, and also there exists co-compact one by Borel. However, such a group cannot be discontinuous group for homogeneous space G mod H, because if this double coset space is a Hausdorff, then gamma cannot be arithmetic. Otherwise, because arithmetic group acts on G mod H ergodically if H is non-compact. So we have to find some other smaller subgroup gamma to be discontinuous groups. So so far this is what we have already observed, namely, but the feature is that if H is non-compact reductive subgroup and G is reductive groups, then G acts isometrically on G mod H endowed naturally pseudo-Riemannian structures, but these actions cannot be proper as far as H is non-compact. And so the idea of the standard quotient is to find some other subgroup acting properly in the following diagram. So namely, try to find a nice subgroup that acts properly. And then any discrete group gamma inside G prime acts automatically properly discontinuously. And so, for example, if gamma is in addition torsion free, and then quotient space is smooth manifold. And if there's such a reductive subgroup acting properly, we call the quotient space is standard quotient. So this quotient is the standard quotient if gamma is contained in a reductive subgroup acting properly. And then one can observe a simple but powerful theorem as follows. Namely, such a homogeneous space admits a co-compact discontinuous group if we can find the reductive subgroup G prime acting properly and compactly on this. for example, by applying this theorem, of course, any Riemannian symmetric space satisfies the previous assumptions. But also, as we have seen, that the odd-dimensional anti-digital space satisfies the previous assumptions. So there exists a compact standard quotient. And also, there exists a 7-dimensional complex manifold, complex manifold, which is locally isomorphic to this quotient. And also some other pseudo-Kähler manifold, which is locally isomorphic to this one. There's a compact quotient. But there are some other compact quotient with different geometric structures. And these examples obtained by using the properness criterion that we have seen theorem A. And also, in this talk, I don't mention, but also there's a compactness criterion, which also is computable. And then by using this, we can find a list of such homogeneous spaces. And so there are some further list of satisfying this compact quotient, existence of compact quotients. And very recently, 2 groups, one is by Tojo, and then the other is a Polish group, Bosensky and Torare and some others, prove that the list is exhausted. And then I'm answering to the questions that it's bold questions that if reductive homogeneous space admits a compact discontinuous group, then this admits a compact standard quotient, namely, if Z mod H admits some compact quotient, then we can find some reductive group acting properly and co-compactly. And evidence of the conjectures is obtained by various methods obtained by, so there are many obstructions of the existence of co-compact lattice developed for the last several decades. Calabi, Marcus, Wolf, Kulkarni, and myself, and Ono, Benoit Labrie, Zimmer, Moses, Margus, Shalom, Okuda, Sorozan, Kassel, Moritas, and some others. Some are using properness criterions, and some are using cohomological obstructions, and some are using Ratner's orbit closure theorems or non-commutative ergodic theorems, so on. So there are many different obstructions, but all of them support this conjecture so far. But this conjecture is still open. And this conjecture applied to the special case implies the constant curvature case. But this is still open. Okay. Okay, so this is about brief summary about existence obstructions for compact forms. So this is kind of the constructions of the instrument. But this is not still an instrument. So to make it a music instrument, then we want to have a change of the length of the strings to have a music. And so now let us discuss about deformation theory. Okay, so by deformations, we mean that we fix local geometric structures given by homogeneous space G and H, and also abstract structure, fundamental groups. So we fix gamma, but then we deform homomorphism gamma into Z. So this we call deformations up to some isomorphism classes. And so the idea is to vary an injective homomorphism by fixing gamma and Z and H. And then we want to say that this double concept space X mod gamma via the phi is a deformation of X mod gamma up to some isomorphism. Then, of course, there are some 2 major problems. One is that there exists or not non-trivial deformations. And even if gamma, there's deformations of gamma inside G, then deformations of gamma may destroy proper discontinuities. So we have to understand these questions to say deformations. Okay. But in our setting that we at least have some nice compact quotient that we call standard quotient, namely taking some subgroup acting properly and take gamma inside L. Then first thing is try to deform gamma inside L, but then there's not enough room for gamma to be deformed inside L. For example, if L is a simple Lie group, and then except for SL2R, that there's no interesting deformations of gamma inside L. This is a Selberg wave rigidity. And so we want to extend the gamma deformations inside Z. Then there exists a larger room for gamma to be deformed in Z. However, we have to be careful after deformations that this deformed actions is properly discontinuous or not. So here's some simple examples. We consider the actions of Z on R by translations. And then if A equal 1, this is just the translations. And but if we perturb a little bit of these coefficients, and these perturbations can be achieved inside the affine transformation group. So this is also formulated in the D group languages. But then even a very small deformations, the double coset, the coset space is normal Hausdorff. And so this means that very small deformations of proper actions may not be properly discontinuous. So this is the bad features. However, Goldman's made a very nice conjectures for the three-dimensional anti-de Sitter space that if gamma is standard quotient, and then small deformations would keep the proper discontinuity, so that the quotient is still a manifold after small deformations. And Goldman's conjectures turns out to be true. And again, that this proof not only three-dimensional anti-de Sitter space, but also for higher dimensional cases, this small deformation in the semi-simple setting is true. And this was proved by using properness criterions. And so this gives a deformation theory for higher dimensional case, and developed further by many other people. Okay, so this is a deformation theory. And so not only three-dimensional complex manifolds, and but some of gammas still has a rigidity theorem, like in the Riemannian case. And some others has a flexibilities, namely has a non-trivial deformations, namely there exists a co-compact lattice for which some deformations includes the Zaleski dense subgroups still acting properly discontinuously. And some of the list will be appear in the paper soon. Okay, so this is quite summary of what is known about preparations of the geometry. So that we have some of them have a nice compact forms or finite volume ones. And then some of them allow some non-trivial deformations, namely a kind of a higher Teichmüller theory for homogeneous space G mod H for this gamma. And then we want to listen to this music instrument, namely spectral analysis. And so now we want to give this latter half. And first, I'd like to talk about new phenomena that never happened for the traditional Riemannian case, but happened for the pseudo-Riemannian case beyond the Riemannian setting. And so, but this is a general questions. So we have a general setting, and suppose gamma is discontinuous group, so that it is a covering. Then any invariant geometric structures can be pushed forward by this covering map. And also differential operators, which is invariant, can be pushed forward. and we call it intrinsic differential operators. For example, if it is covering of the pseudo-Riemannian manifolds, then Laplacian on the above pushed forward to the lower part is the same Laplacian. So this is generalizations of such operators. Then we want to, if this operator is, for example, extend to the self-adjoint operators, and then we want to understand eigenvalues of these operators, and also wish to construct joint eigenfunctions, and also try to find the spectral theory of these ones. And in the pseudo-Riemannian case, that Laplacian is one of such operators, but sometimes there exists another higher differential order differential operators, which is algebraically independent of the Laplacians. And so also you want to include such operators. So we want to understand if such a differential operator is commutative to each other, and then we want to find joint eigenfunctions and also understand the joint eigenvalues. So this is what we wish to understand beyond the Riemannian setting. Okay, now I explain this what we call universal sound. This is the new phenomenon in the pseudo-Riemannian case. So we know classical theory for Riemann surface, compact Riemann surface, that we consider compact Riemann surface, and then we consider Teichmüller space. Then each eigenvalue, for example, first eigenvalue, second eigenvalue, third eigenvalue, such an eigenvalue may be considered as a functions on Teichmüller space. And then such an eigenvalues cannot be constant functions on Teichmüller space, namely eigenvalues vary as functions on Teichmüller space. So this is a usual setting in the Riemannian geometry. And so this corresponds to the case that if we consider music instrument, and then shorter strings produce a higher pitch, and thinner strings also produce a higher pitch. So this is a common sense in the Riemannian geometry. But we discovered that a new phenomenon in the Lorentzian case as follows. Consider three-dimensional compact anti-de Sitter manifold. And then we consider the Laplacians. And then there exist countably many eigenvalues, L2 eigenvalues, which are locally constant as functions on higher Teichmüller spaces. So it's completely opposite situations. So in this case, it's a Lorentzian manifold. So Laplacian is no more elliptic differential operators, but it is hyperbolic differential operators. And this is stable, as I mentioned, that this does not vary under deformations of anti-de Sitter structures. And in this case, that we have large dimensional Teichmüller space for this variations of anti-de Sitter structures. But some of the eigenvalues are constant. This we call universal sound of this new music instrument. So, and the universal sound of anti-de Sitter manifold. And this is three-dimensional results, but actually that we prove such a theorem for higher dimensional semi-simple symmetric space satisfying certain rank conditions. And I don't write down its formulations in full generalities, but give some another typical examples. So typical examples includes group manifolds. And for group manifolds, that this has been studied a lot in connection to the automorphisms. And so we may compare with some classical theorems. So suppose that G is reductive groups with high Chandler's rank conditions. Then our theorem, special case in this setting, says that take any torsion-free discrete group gamma, then any high Chandler's discrete representations of the group with sufficiently regular parameters sits inside in the space of the gamma periodic L2 functions on this space. And such theorems is known when gamma is an arithmetic group, and with some additional conditions, like by Kazan, Jens Lee, and George Wallach, and Claude Robespierre, and they are different methods, but they consider the arithmetic groups, and then not exactly of this form, but replaced by some congruent subgroup gamma prime, possibly depending on lambdas. But actually, we don't have to replace gamma prime. And also, this theorem is true not only for arithmetic groups, but for any discrete group. And even gamma is covolume infinite, still this result is true. So this is so our theorem is completely using different method. And this is some features of our method. And the idea of the proof is the following. And so first we construct non-periodic eigenfunctions, and then by different geometries, and then consider holomorphic extensions, and then restrict to other real forms. And then and step 1 and step 2 are not new, and the step 3 is new. So then we, from this non-periodic eigenfunctions, we construct periodic eigenfunctions. And for this, we consider generalizations of the idea of the Poincare. And to make justifications, we need both new geometric estimate and analytic estimate. Such as geometric estimate is like Kazan-Margulis theorem, and also myself and Benoit and Cassel myself. Some geometric estimate that I recall some of the features next slide. And also, we also need some analytic estimate of the eigenvalues, eigenfunctions at infinities. For this, that we use some Sato, Kashira, Kawai, and Oshima's works for microlocal analysis and system of partial differential equations with regular singularities by making some compactifications of the manifold. And for geometric estimate of the proper actions that we consider counting. So this left-hand side is symbolically write classical traditional counting problem in the Riemannian setting. So we consider counting of the lattice in a ball, or more generally, we consider Riemann manifold, and then consider the orbit of discrete group of isometry, and then count its orbit inside the fixed ball, and then try to understand, for example, how many points in here depending on the radius. So in the beyond the Riemannian setting, that we don't have a natural notion of the ball and metric, but still we may think of some pseudo ball, and then there are several ways of the generalizations of the classical counting problems. One is by Eskin, Macmillan, and Hio, and so on. They consider lattice of gamma, and then consider very special orbit for which gamma x is closed. So generic orbit is not closed, and so but there are some special point for which gamma x is closed. So this is one way of the generalizations. But on the other hand, what we need is that we need not only a special point, but for all points x. And we don't take lattice, but we take discontinuous groups. And then we need some estimate of the counting, locally uniformly with respect to the point x, and also locally uniformly with respect to the deformation of the gamma. And this can be achieved by using the properness criterions as a method. And this is one of the tools for constructions of periodic eigenfunctions. Okay, so now this is a new phenomenon that some of the eigenvalues not stable under small deformations of the geometric structures. And so, so this means that if we have a new geometries, new instrument, and then try to hear the sound, then some sound is constant even if we change the kind of the length of the strings, but still the sound is the same. But not all. So some of the sound is the same. So this is what we call universal sound. And then the last topic is to capture all the sound. Some are unstable sounds, and also some are continuous spectrum. Try to capture all sounds. Then we need some new theory, new method to capture all sounds in this beyond the Riemannian setting. And the key idea is branching problems in representation theory. So branching theorem is the following. Given a representation of the group to a vector space V, and then consider its subgroup G prime, and then this restrictions is considered as a representation of the subgroup. For example, fusion rule of the tensor product, namely, we consider two representations of the same groups, and then two representations may be considered as representations of the direct product group on the tensor product of vector spaces. But also we can consider its diagonal subgroups. So this is a usual tensor product, and its reductive decomposition is called fusion. And by branching problem, that we want to understand how the restrictions pi to G prime behaves as a G prime modules, such as explicit decompositions, but more generally, we want to understand the behaviors. And in the case of the finite dimensional group for compact groups, such a problem is well studied and as a combinatorial problem. But on the other hand, when G and G prime are non-compact like GL and reductive groups, then this problem is very difficult, and the explicit branching loss is extremely difficult to find. But still, for the last 2-3 decades, a large development of the branching problem has been developed. And now we use this as a machinery to capture all the sound of new geometry. Okay, so this is our previous setting that we consider standard quotient, namely take an appropriate subgroup, reductive subgroup acting properly, and this subgroup can be detected by using the theorem A, this properness criterions. And then we take some discrete subgroup gamma inside this subgroups. So this is stations of standard quotient that we have already explained. Then we assume one more additional assumptions, namely, its complexifications of GC prime on XC is spherical in the sense that Borel subgroup, so something like upper triangle matrices, has an open orbit in the complexifications. This is also easy to check which cases exist, and actually we have a classifications of all such stations. Under these assumptions, surprising things happens in representation theory. Namely, assume these two conditions are satisfied, then any irreducible infinite dimensional representations of the group Z realized in the space of the functions on X, smooth functions or distributions, whatever, then such representations viewed as a subgroup Z prime split discretely into Z prime reduced modules, namely continuous spectrum disappears. So this is discrete decomposable. So this is so such a geometry gives a very nice stations of representation theory. And if there's no continuous spectrum, then we can understand much better each pieces, irreducible pieces of these representations. And so we can go further. And so the situation is the following, that under our geometric assumptions, we have theorem D that has a no continuous spectrum. And actually, we can understand not only abstract discrete decomposability, but also we can understand detailed informations of the representations by discovering some new structure theorem of the ring of differential operators in this geometry with respect to the certain fibrations. And then we can now reach to the final goal, namely spectral analysis of the double set space beyond the Riemannian setting. So we recall our notations. So this is our setting of standard quotient, and then also we assume sphericity assumptions. Then we want to understand eigenspaces of invariant intrinsic differential operators, and including Laplacians, but some of the geometry has higher differential operators algebraically independently with Laplacians, and so we want to consider all differential operators. And actually, in our setting that this space is commutative, and so we can think of the simultaneously eigenvalue problems. And so lambda d is joint eigenvalues. And then what we proved is following theorem. This is a joint paper with Kassel and myself, and this is quite long papers. It is to appear in lecture note in mathematics in spring. And this says that there exists a measure mu on the space of joint eigenvalues, and this space is well understood. So this space is Euclidean space modulo certain finite groups, and then there exists a Borel measure on this space, and then there exists a measurable family of maps from the space of compactly supported smooth functions on this double coset space, so locally homogeneous spaces beyond the Riemannian setting, to the space of joint eigenfunctions. So it's a kind of the Fourier transform, such that any functions can be expanded into the direct integral of the joint eigenfunctions. So this is a kind of the Fourier transform theories. And also the Plancher's time theorem holds for this new Fourier transform for these double coset spaces. So this in particular shows that Laplacians with indefinite metric on this space is essentially self-adjoint, which is non-trivial even in this case. Okay, so in this talk that I have explained, about as a warming up local to global problem beyond the Riemannian setting, and then given local geometric structures given by pair of Lie groups. Special case is a constant Kobayashi space, but also we consider more general setting. And then gamma is a discrete group, but usually this action is not necessarily proper discontinuous. And so we first discuss about properness criterion, proper discontinuous criterions for this one. So this allows us to give a constructions of the nice geometry, sometimes are compact ones, but also give some obstructions for nice geometries. But some of them have compact forms or finite volume ones. And then also some of them has continuous non-trivial deformations. So this we regard it as a new geometry, so new music instrument. And then we try to hear the sound, so namely develop the new spectral analysis on this new geometry. And first, we discussed some phenomena that never occurred in the Riemannian setting that we call universal sum. Some of the L2 spectrum is stable under the deformations, but some other spectrum vary depending on the point of the higher Tahimian space. Then finally, we try to capture all sounds in the standard cases. And for this, the machinery is to utilize branching theory of unitary representation, infinite dimensional representations to non-compact reductive subgroups. So this is what I have explained in this talk. So I think time is over, and thank you very much for your attention.
Thank you for the wonderful talk. Any questions?
Thanks for the talk. For theorem D, you mentioned, so you were studying smooth functions on X in theorem D.
Study what?
You were stating the result theorem D in
Yes.
in the space of smooth functions. So what happens if you try to do L2 functions in those theorems?
Theorem D.
Yeah.
Yes. Okay.
What if we want to understand L2 functions, the L2 space on X?
And what is the group?
Like in this setting.
Yes. And then your question is.
So if we replace C infinity X by L2 of X.
Oh yeah, this is also true.
Also true.
Yeah,
Okay.
and but actually, so this is true for distribution space. So some of the unitary representations sit inside distribution space, and then still this decomposability holds. And actually, that I formulated it in terms of the algebraic representation theory, and then one can form it in smooth functions. But if we consider analytic representation theory, and then the right space is distributions.
So you're saying that this theorem is actually about, say, Harshanja modules? Is that
And
right?
so what I'm saying that the theorem can be formulated in an even stronger way.
Okay.
And then whatever the function space, hyperfunctions or distributions, and still it is a discrete decomposer.
Thank you.
You can.
Actually, I want to ask, here your H is not a spherical, right? Subgroup, right?
Our H is for the final theorem, theorem E, H is spherical. Spherical subgroups.
You assume that H and G,
G mod H is spherical.
G prime and H are both spherical?
G mod G prime is not spherical, not necessary. In many cases, by classification, it is spherical.
But then I don't understand what you mean by G
spherical.
prime,
Okay,
G prime acts spherically on
GC prime acts spherical on XC, means that Borel subgroup of GC prime has an open orbit in XC. So it's not different from G mod G prime is spherical. It's different.
I see. So and also your gamma is an arithmetic subgroup of
any
G prime. Any subgroup of G prime. Okay.
So even gamma is trivial. This is a new theorem.
I see. Okay, thank you.
Yeah.
Okay, maybe another question.
Yes.
Is that whether is it possible to develop some kind of trace formula on this?
Yeah, that would be a new problem, I think. So I think there's a chance.
There's a chance. I see.
Yeah.
Okay.
In particular, in connection to the setting of theorem E, there's a lot of possibility to generalize what was known in the Riemannian case.
I see. Okay, thank you.
Yeah.
More questions?
Hi, Professor. Is it possible to say estimate the spectral radius of the first eigenvalue? The first eigenvalue, or estimate the spectral radius of, like, in the classical Riemannian case?
So the first eigenvalues is a difficult notion because in this situation that eigenvalues, the infimum of eigenvalues is minus infinity, and then maximum is plus infinity. So supremely, so it's not elliptic differential operators like Laplacians, and it's a hyperbolic operators. But the interesting thing is that, for example, in the case of the three-dimensional anti-de Sitter space, then positive eigenvalues are more or less stable, and the negative eigenvalues vary. So in this sense, one may formulate some notions of first eigenvalues, but I do not have precise formulations.
So still to be discovered.
Yeah.
Thank you.
Because of the time limit, let's end the speaker again.
Thank you very much.